Today's notes covers the chain rule. So before we jump into new stuff, let's just relate this to what you did in Calc 1, like Calc AB or Calc BC. In Calc 1, you were often given some function in terms of x, and then that x is a function of t. So this was a composition. So you had y of x of t. If you wanted to find the derivative for y in terms of x then, or in terms of t rather, so you wanted to find the derivative of y in terms of t, you found the derivative of y in terms of x, and then you found the derivative of x in terms of t. That was the chain rule. Today, things are going to get a little more complicated because instead of having one independent variable, so the t or the x, we're going to have multiple. So we're going to be looking at functions of several variables. So let's take a look. Let's say that now we have some function z that's a function of x and y. X can be defined in terms of t, and y can be defined in terms of t. So then, if we want the derivative of z with respect to t, we'll have to take the derivative with respect to x, then t, the derivative with respect to y, and then t. Now, one thing I want us to notice here is these are both partial derivatives, and those are partial derivatives because z is defined in terms of x and y. These are just normal derivatives. They're not partial because x and y are just defined in terms of t, only one variable. So partial is more than one variable. Whereas I'm going to just call it non-partial is only one variable. So let's take a look at an example. Consider z is equal to x squared y, subtract y squared. X is sine of t, and y is e to the t. We are finding dz dt at t equals 0. Okay, so first thing, dz dt is not a partial derivative, so I want us to pay attention to that. dz dt is not a partial derivative. So dz dt is going to be equal to, using that chain rule above, I need to find the partial with respect to x, which is 2xy. Then I need to find the derivative of x with respect to t, so that's cosine of t. Then I'm going to find the partial of f with respect to y, so that's x squared subtract 2y. And the derivative of e to the t is just e to the t. So one thing that you're going to notice is we want our derivative in terms of t, but we still have x and y in it. So now what I'm going to have to do is replace my x and y with what I have x and y defined as. So what that gives us is 2 sine of t, cosine of t, e to the t, add sine squared t, subtract 2e to the t, multiplied by e to the t. So that is our dz dt. So that is telling us the rate at which z is changing as t is changing. And then if I want to evaluate dz dt at t equals 0, if you trust me, I'm going to tell you that you end up with -2. So all I did was take that line above and substitute in t equals 0. So that's the first example. Now I want to take a look before we go on at how you would do this if you didn't have the chain rule. So if you didn't have the chain rule, what you would have to do is you would have to start by finding z in terms of t. So we would start with this equation, and we're going to substitute in x and y. So we would get sine squared t, e to the t, subtract e to the 2t. Now we can take the derivative with respect to t. On this first term, I'm going to need the product rule. So that would be 2 sine of t, cosine of t, e to the t, plus e to the t, sine squared t, subtract 2e to the 2t. And we are going to notice that this is the same as above. In this case, you could argue that it might have been easier to use this second method without the chain rule. That's not always going to be the case, though. So things are going to get a little bit more complicated. We're going to have more variables, and that's what we're going to look at on the next page. Okay, so this idea is going to extend to any number of variables. So let's say that we have some function u that is a function of n different variables. So x1, x2, all the way to x of n. And each x is a function of multiple variables as well. So then what we're going to have to do is we take the derivative of each u with respect to x, or u with respect to each x, and then x with respect to each t. And then so on and so forth. Okay, so I think that's a little complicated. I will tell you, I do not memorize this. Instead, what I often do is I use a tree diagram. So anytime we can't use that initial chain rule that's on the first page because things are a little complicated or we have a lot of different rules, what you're going to do is jump to a tree diagram instead. So I'm going to show you an example. Let's say that we have z is some function of x and y are both functions of t. So a way to start with our tree diagram then is z is a function of x and y, x is a function of t, y is a function of t. Okay, so then here I have two different options. This indicates a partial derivative. Here where there's only one and here where there's only one, that is not a partial derivative. So let's say that I wanted to get to the end of my tree and I wanted z in terms of t. Okay, so I have two ways I can get to t. I get to t this way and I get to t this way. So that first path to the left, I have the partial of z with respect to x, and then I took the derivative of x with respect to t. Then on the right side, I took the partial of z with respect to y, and then I only have one option, which is dy dt from there. And that is the same as the chain rule that we wrote on the previous page. That is going to help us, like when we see an example in 2 where we've got a lot more variables. So let's try another one of these. In example 2, we have z is some function of x and y, and x is a function of u and v, and so is y. We are finding dz du and dz dv. So first thing, before we look at any tree diagrams, I want you to notice that this is just a partial derivative. Partial and partial. And that's because z is a function of both u and v. And you'll see that in the tree. So to start our tree, we would say z is a function of x and y. X is a function of u and v. Y is a function of u and v. So you'll notice at every point on the tree, we have two options, which means they're all going to be partials. So if I go this way, it's a partial. If I go that way, it's a partial. That's a partial. That's a partial. All of them are partials. So if I'm looking for the partial of z with respect to u, so I need to get down to u and I need to get down to u. So I would take this branch, and I would add to that, taking this branch and this branch. So that would be the partial of z with respect to x times the partial of x with respect to u, and then it's the partial of z with respect to y, and the partial of y with respect to u. So that would be the chain rule for dz du. Now, if I want the partial of z with respect to v, same idea. I'm going to go this way, but then v, this way, and then v. Because at each of those branches, I have two options. They're all going to be partials again. So I have the partial of z with respect to x, and the partial of x with respect to v. And then I have the partial of z with respect to y, and the partial of y with respect to v. And so those are our two chain rules. So normally what you would do is you would actually have the functions, and this tree would just be a way for you to see how you would find your derivative. So let's take a look at example 3, where we're actually going to use the tree diagram that we come up with. Okay, so consider z is equal to 2xy. We have x in terms of u and v, and y in terms of u and v. We are finding the partial of z with respect to u. Now, you are not required to do a tree diagram. So if you know how to find that derivative right away and you don't need a tree diagram, totally fine. For me, it's helpful. So what I would do is I would say, okay, I have z that's defined in terms of x and y, x is defined in terms of u and v, and y is defined in terms of u and v. So if I want the partial with respect to u, I got to get back down here. So the partial of z with respect to u is going to be the partial of x with partial of z with respect to x, and then the partial of x with respect to u. Then I have the partial of z with respect to y, and the partial of y with respect to u. So that's what we did on the previous example. So now what we're going to do is we're actually going to fill this in. If I take the partial of z with respect to x, I get 2y. Partial of x with respect to u would be 2u. Partial of z with respect to y would be 2x. And the partial of y with respect to u would be 1 over v. Now, I want this, though, in terms of u. I don't want this x and y in here. So what I'm now going to do is substitute in for x and y. Y, we said, is u over v, so this comes from here. And then we have 2u. X is u squared plus v squared. And then we have our 1 over v. Now, I would like this to look a little bit nicer. So if I end up simplifying, I'm going to have 4u squared over v, add 2u squared, add 2v squared over v. So my partial then of z with respect to u is going to be 6u squared, add 2v squared over v. Now, it's okay that we have u and v, both u and v in our derivative. And that's because if x and y are in terms of u and v, if we were to substitute them in, our initial function would be in terms of u and v. So that's not a problem. But, of course, we should not have x and y in our answer. Okay, so next example. Example 4, we are finding dw dx if this is w and we have y and z in terms of x. When it says find a rule, I don't mean find the chain rule. I want to know what is the actual derivative. And you'll notice that this is a full derivative, not a partial. So if you're feeling pretty good, this might be a good place to stop the video and try it on your own. If you don't feel like doing that and you just want to stick around with me, you are certainly welcome to do that as well. So I'm going to start with my tree diagram. W is defined in terms of x, y, and z. Y is defined in terms of x, and z is defined in terms of x. So this one is a little bit different. If I want dw dx, I have to end up at x. So I have 3 different paths I could take. Okay, so dw dx, if I go the first path, that's a partial. That's a partial of w with respect to x. So notice this partial is different from what I'm looking for. Okay, so then in the middle, I would take the partial of partial of w with respect to y, and then the partial of y with respect to x. And for the last one on the right, I would take the partial of w with respect to z, and the partial of z with respect to x. Okay, so now actually substituting those in. Partial of w with respect to x is just y. Partial of w with respect to y is x add z. Partial of y with respect to x is cosine x. Partial of w with respect to z is just y. And then I have e to the x. Okay, so this is not a partial. This is a full derivative, not a partial, which means everything needs to be in terms of x. So I have to replace this y, this z, and that y. So I get my dw dx is equal to sine of x, add x plus e to the x, cosine x, add sine x, e to the x. And that's our answer. Hopefully, if you tried that one on your own, it went well. So here are a few notes for you. I want you to express your answer in terms of a single variable, or like example 3, 2 variables. So in this example that we just did, everything was in terms of x. In the example before, everything was in terms of u and v. That being said, WebAssign doesn't require you to go that far. So when you do your work on WebAssign, you can stop at this line right here. You don't need to further substitute. In fact, I believe if you were to put this blue answer in on WebAssign, it's going to mark it wrong. So once you do your first chain rule, leave your answer like that. You need to remember the difference in expectations. So I expect you to go farther than WebAssign does. Okay, so at this point, that is the basics of the chain rule. We're going to end this video with 2 more examples relating to implicit differentiation. Okay, so this next example, let's consider that we have this function right here that's written implicitly. Let's say that I wanted you to calculate dy dx. What would you do? Well, before, in Calc 1, you would use implicit differentiation. So you would say, okay, the derivative of y cubed is 3y squared, and then that gives me dy dx, and then I have 2y dy dx, subtract 5 dy dx, subtract 2x equals 0, and then you would factor out your dy dx, and you would move some things over and divide, and you would end up with 2x over 3y squared, add 2y, subtract 5. So that's what you did before. We're going to do it a little bit differently now. So let's start with that same equation. So what we're going to do in this equation then is we're going to take this whole left side and we're going to call that a function of x and y. And we are going to set that function equal to some value c, which is that number there. Okay, so now what I know, tree diagram, I have f that is some function of x and y, and I want y to be defined in terms of x. Okay, so we're treating this now just like we did in Calc 1. We're saying y is some function of x. So using our chain rule then, if I want to find dy dx, I'm going to take the partial of f with respect to x, and then I'm going to take the partial of f with respect to y, and y with respect to x. So then, if I isolate dy dx, I get the negative partial of f with respect to x over the partial of f with respect to y. So if we go back to this equation we have, our dy dx then, left side, if I take the partial with respect to x, I get negative 2x. If I take the partial with respect to y, I get 3y squared plus 2y, subtract 5. And what we notice that makes us happy is we get the same answer as what we did in Calc 1. Okay, we've got one more trying that. But before we do that, fun fact for your homework that you're going to need. It's the way to find an area of a triangle that's not a right triangle. So just so you know, you're going to see a problem in your homework where you're going to need that formula. So just keep it in mind. Okay, last example. What happens if we're using implicit differentiation and we now have 3 variables instead of 2? We are finding the partial of z with respect to x and the partial of z with respect to y. These are both going to be partials because there's no way for us to get a function of z just in terms of x or y. Okay, so we're going to approach this the same way that we did before. This all I'm going to call f of x, y, z. So now I have my function of x, y, z is equal to x squared add y squared add z squared. And I'm setting that function equal to c, c being 1 in this case. Okay, so if I have a tree diagram, I have f in terms of x, y, and z. And z I'm going to define in terms of x and y, since those are my 2 independent variables. Let's return to our equation then. We have f of x, y, z is equal to c. So if I want to take the derivative with respect to x, using my chain rule tree on the left, I have the partial of f with respect to x, add the partial of f with respect to z times the partial of z with respect to x, and the derivative of c is just 0. So then my partial of z with respect to x, if I solve for that above, I'm going to get the negative partial of f with respect to x over the partial of f with respect to z. Likewise, if I did the same thing for partial of z with respect to y, which we were also asked for, we would get the partial of z with respect to y is equal to negative partial of f with respect to y over partial of f with respect to z. And that's just the rule, the two rules. You don't need to memorize that, or you don't need to derive that. If you want to just memorize those results, great. If you want to derive them, great. But if we now go back to our original equation, which we defined our function that way, we get the partial of z with respect to x is equal to negative 2x over 2z. So the partial of z with respect to x is equal to negative x over z. Likewise, the partial of z with respect to y is equal to negative y over z. And that's just using these two formulas above. Now, we also could have approached this equation implicitly. So again, our equation is x squared add y squared add z squared equals 1. As a reminder, we want the partial of z with respect to y. And just some other facts, we know that if we take the derivative of y with respect to y, we're going to get 1. If we take the derivative of x with respect to y, we're going to get 0, and that's because x and y are independent. So if we take the derivative with respect to y, we're going to get 2x partial of x with respect to y plus 2y partial of y with respect to y, add 2z partial of z with respect to y is equal to 0. Like we said, partial of x with respect to y is 0, partial of y with respect to y is 1. So that gives us 2y add 2z partial of z with respect to y is equal to 0. So solving, that gives us the partial of z with respect to y is equal to negative y over z, which is exactly what we got above. So you have two options on this last one. If you have an implicit equation, so it's not a function, but it's an equation, you can remember these two formulas that we derived above, or you can approach the equation implicitly. If you have any questions, please make sure you write them down and bring them to class. See you soon.